Thanks, Edson. My name's Jason Patrick. As Edson introduced, I'm the technical director at Elect Software. I've been in the software business for almost 20 years, and I'm an electrical power engineer. I've led the development of cable sizing software and ongoing development of power system software. This is a 1 hour technical presentation on low voltage cable sizing calculations. I'm the presenter. Edson is here. We will be answering questions at the very end. Please type your questions in the chat. So, who is Elect Software? Very quickly, we develop power systems, modeling software, calculation software. Our main products are Elect Cable Pro Web, which is low voltage electrical design software. That complies with Australian standards, British standards, and soon to be IEC standards. We also have earthing system design software, and one of our specialties is HV cable rating calculation software as well. We're the world leader in those areas. We're headquartered in Sydney, where we do our research and development. But we're also an internationally distributed company. So this is a photo of some of the Sydney team members, recent photo. So our customers include, you name it, a lot of the large companies down to the smaller contractors and electrical installers. So the content of this presentation at a high level, I'm obviously going to talk about low voltage cable sizing standards. This presentation will cover Australian standards, British standards, IEC standards in one presentation. The principles across those three standards are exactly the same, so they're universal. I'll briefly touch on the differences between low voltage cables and HV cables, just for interest. I'll talk about how we properly size active conductors, talk about the coordination with protective devices, temperature limits for cable types, derating factors, equations for voltage drop. I'll share some expert tips on voltage drop calculations, short circuit ratings, neutral and earth cable sizing, harmonics and economic cable sizing. Look, it's a lot to cover in 1 hour, obviously, but I think that everyone from beginner level to expert is going to get something meaningful and useful out of this presentation. I guarantee that. And there'll be, at the end, there'll be a worked example. I'll actually go through a sort of a hand worked example with the equations, so you can understand all of the steps involved in these sort of calculations. Also to refresh those who are already experienced. And then I'll give a brief overview of how to do it in software. That's going to be very fast because it's very quick to do these sort of calculations in software. But importantly, at the end, I'm going to introduce to you a website where you can access our cable sizing calculators for free. So stick around for that. And also at the very end, there'll be a link and a QR code that you'll need to use to fill out to get your certificate of attendance if you need it for CPD points or for your resume. Finally, I'll draw some conclusions and there'll be a question and answers at the very end. The calculations, the software that we're using is Elect Cable Pro Web software. Is for low voltage electrical design, network design, cable sizing, obviously to multiple standards, maximum demand calculations, voltage rise, cable pulling calculations, as I mentioned, network designs with switchboards, protection coordination, and arc flash. You can get a free trial of that software at elect.com for 14 days. Low voltage cable sizing standards, it's mixed up a little bit here, and I will explain. So there's obviously some IEC international standards. Now, Australia and British standards are fundamentally based on IEC standards, international standards, European standards. So there's IEC 60364-5-52. That's the International Cable Sizing Standard. It's structured very similarly to AS NZS 3008. It has a bunch of tables, derating factors. The method is fundamentally the same. So current capacity, voltage drop, short circuit ratings. Same with BS 7671. That's their AS 3000 combined with 3008 in one book. But again, they have, instead of derating factors, they have correction factors. Again, the principles are the same. There are tables of current capacities. Derating factors, there's voltage drop calculations, and short circuit ratings, just the same. The NEC, American Standard, I'm not going to get into in this presentation at all. Obviously, it does exist. The main difference is really in the units, and the AWG cable sizes are a little bit different. But again, I'm not going to go into details into the American NEC standard for low voltage cable sizing. There are some alternative specifications. Now, these low voltage cable sizing standards, the tables that you see within those standards, the current rating tables, they are derived using calculations that are based on IEC 60287. That's a very extensive series of standards. There are 9 parts to that standard. And so you'll actually find, if you open up the front of BS 7671 and AS 3008, they are all referring to calculations based on IEC 60287. So to do those sort of calculations, if you had a situation that was outside of the conditions covered by those low voltage standards, or if it's a very important installation of low voltage cables, I would recommend that you use a software package that's based on IEC 60287, like our Elect Cable HV software. I've also listed, there are a couple of standards around that list medium voltage cable ratings. Those are listed there on the slide there as well. But again, those are based on calculations from IEC 60287, that method there, which is quite extensive, and or more advanced software calculations. So what's the difference between LV and HV calculations? Because as I mentioned, all these calculations are based on IEC 60287, that method there. And that method can calculate the current rating for low voltage cables and high voltage cables, just the same. The model is the same. The calculations are fundamentally the same. It's just the construction of the cable that's different. So low voltage cables are much simpler. They have a conductor, insulation, and a jacket. Pretty much. There are maybe some additional shielding layers, but these are rare. There may be some armor. The difference with high voltage and medium voltage cables is, and you'll see the image in the top right-hand corner, there's more layers. We have higher electric field strength, so we need more shielding layers around the conductor, around the insulation. You'll see sheaths and screens and armors, etc., and many more layers. So thermally, electrically, they're more complex. That's really the only difference. So low voltage calculations and the low voltage cable sizing standards are based on these simpler types of low voltage cables. So how do we size a low voltage cable? Well, there are 3 fundamental factors to sizing a low voltage cable, and we need to meet all of them, all of the criteria, including current capacity that ensures the cable doesn't overheat during operation. That's the first criteria. The second, so that current capacity usually dictates the size when we have large load currents. Then the second criteria is voltage drop. This prevents excessive reduction in voltage over long distances. This usually dictates the cable size when we have when we're running cables over long runs, long lengths. And then there's short circuit rating or short circuit performance. This protects the cable during fault conditions. This dictates the cable size, rarely dictates the cable size, but it can when the cable run is short and when the fault level is quite high. It's a rare condition, but I'll show you one of those conditions when we talk about short circuit ratings. So to size a low voltage cable, active cable, we need to meet all three conditions. The cable size must meet all of the three criteria. There are additional factors that we need to consider for minimum active cable size, including mechanical strength, minimum size to meet mechanical strength, the installation conditions, temperature limits, and also energy efficiency. I'll talk about that as we go. In terms of the calculations, if you look at it from start to finish, sizing an active cable, there's actually quite a number of steps involved, some involving human interaction or human input, and this is sort of a flow. And the yellow boxes are the three criteria that I mentioned. Now there's human and computer mostly. Most often we do these calculations using computers because they're iterative. So we get an active size that meets current capacity, but then we've got to work it out to meet voltage drop. And we may need to increase the size in that step. So we've got to go back and recalculate the current capacity and so on until we meet all three criteria. That's why we usually use computer calculations. It also means that we don't have to remember complicated formulas, and the software has everything inbuilt, all the numbers, all the current capacities, resistances, reactances. We don't make mistakes, and we also get a nice report. But the point is that there are lots of steps to this, to the process, and the three main criteria are highlighted in the yellow boxes. But I guess the real starting point for active cable sizing is the minimum size to meet mechanical strength. So even for current capacity, we can't have a cable size which is smaller than the minimum size, which is dictated by the standards for different cable types and installation conditions. Different standards have different minimum sizes. But even if we have a very low current, we still have to meet these minimum sizes to meet for mechanical withstand reasons to avoid damage. The top right-hand corner is the table from AS3000, which is the Australian standard. Bottom right-hand corner is the international standard minimum size for mechanical reasons, mechanical strength. We also need to coordinate our cable size with the protective device, okay? There are coordination bands or zones here. So the protective device must obviously be rated higher than the maximum load current. Maximum load current IB, protective device nominal rating must be above the load current, or else it's going to trip, right? And the current capacity of the cable must be greater than the rating of the protective device. So in other words, the protective device is there to protect the cable, right? It's to protect the circuit. Otherwise, during a fault or an overload, I should say, the cable is going to get damaged. And we can see an example there in the photo of a miscoordination miscoordination of the design between the cable size and the protective device rating. That could also have been caused by short circuit. The protective device short circuit rating must be higher than the short circuit maximum short circuit of the cable circuit as well. So that's about the coordination between the protective device and the cable sizing. There are temperature limits for these cables, and it mostly depends for low voltage cables and high voltage cables the same. It mostly depends on the insulation type. So the main insulation, whether that's PVC, XLPE, EPR, silicon, etc. There are usually two temperature limits. There's the continuous temperature limit, when it's carrying its normal steady state continuous load. And then there's short circuit or short duration, short time temperature limits. Those are used for the short circuit ratings. It's also highlighted here. This table here is the table of temperature limits for lots of different insulation types taken from AS NZS 3008. Now, it's important to note here that current capacity in this standard is based on the normal use temperature, not necessarily the maximum permissible temperature. So, for example, you have a V90 PVC cable, which has a maximum permissible operating temperature of 90 degrees, according to the manufacturer, right? But the current capacity in this standard has been calculated based on 75 degrees, not 90. Now, the higher operating temperature, the higher current it can carry. Okay, so it's important to note that some of these cables are not calculated to be operating at their maximum temperature. If you wanted to do that, you would need to use like a custom cable sizing calculator like Cable HV. Derating factors or correction factors according to British standards. There are 9 main factors that derate cables, including ambient temperature, depth of burial, thermal resistivity of soil, varying loads, load factor, thermal insulation. Direct sunlight has a very significant impact. Harmonic currents, it's a little bit harder to deal with. I will explain how to deal with it. Groups of parallel circuits, very common, whether those groups are in air or buried groups. You see an example of that in the picture here. And enclosures, they also derate cables. Now, each of the low voltage cable ratings or cable sizing standards includes a number of tables for derating factors. I'm obviously not going to share those in this presentation. There are simply too many of them. What we do with that derating factor is we multiply the derating factor by the current capacity of the cable. Now, if there are multiple derating factors, we combine them. So we multiply them all together to arrive at one derating factor. Now, just remember that derating factors can be higher than 1. You may actually be increasing the rating of the current capacity or increasing the current capacity. For example, it's all based on the standard conditions. So ASNZS 3008 is set up for an ambient air temperature of 40 degrees. But suppose that your installation, you're installing your cables in an environment of 30 degrees Celsius. Well, then you can use the derating factor tables to find a derating factor which is greater than 1, which you can multiply by the current rating in the tables to increase the current capacity of your cables. It's an important tip also is that you can use derating factor tables from different standards. You can look them up and use them together. But it's important to note the base or standard conditions that they're based on, and you need to adjust them accordingly. Say, for example, there's a useful table in the British standards, derating factor table, and you want to use it in the under Australian conditions. You need to adjust it using the tables such that you're considering the ambient temperature in Australia as opposed to the UK. But you can use them. This is the accurate equation for voltage drop calculation. There are lots of different equations for voltage drop. This is the one you should be using. There are simpler ones that you can use by by hand, and predominantly they're taught in schools that can be more easily used by hand, but they're not nearly as accurate. The important point about this equation is that it uses resistance and reactance of the cable, not a simple lookup value. Resistance is temperature dependent. So we also calculate the operating temperature of the cable, and we adjust the resistance because, as I said, it's temperature dependent. And reactance is phase spacing dependent. So you can also adjust reactance. And it also uses the actual load power factor, which I will show has a very significant effect on voltage drop. So the conclusion is always use this accurate formula. And in software always uses the accurate equations. Here's an example calculation of where power factor alone has a very significant impact on the cable size. So it's important to understand your load power factor and to use an accurate value of load power factor. And you can see that just a varying load power factor from 1 to 0.95 increases my cable size by one size from 240 square mil to 300. And there's quite a significant cost increase as a result. Now, power factor, I will mention during my voltage drop tips. Power factor has more of an impact for larger cables than it does smaller cables, smaller cable sizes. And the standard rules, don't forget that the standard rules require you to maintain a power factor of 0.9 lagging or above. So here I'm going to give 10 expert tips for voltage drop calculations. Hopefully you learned something. Voltage drop equation, always use the accurate voltage drop equation that considers cable resistance at operating temperature, reactance, and power factor. For long cable runs to small loads, for long cable runs and to small loads, or not necessarily small, but voltage drop usually dictates the cable size for long cable runs. For short cable runs with low current, the size is usually sometimes dictated by the short circuit rating. Poor power factor has a significant impact on the cable size, especially for large cables. Heavily loaded cables, tip number 4. Heavily loaded cables run hotter, meaning resistance is higher, therefore your voltage drop is higher. Unbalanced three-phase circuits. You need to deal with voltage drop in unbalanced three-phase circuits. So if the conditions or the unbalanced conditions are intermittent on the three-phase system, then you can simply use the load on the highest loaded phase of the three-phase system for your cable sizing. However, if the outer balance conditions are consistent or permanent, then you should calculate voltage drop based on a single phase basis by summing the voltage drop of the heaviest loaded phase with the voltage drop in the neutral. Tip number 6, multi-core cables have a lower voltage drop in general than single core cables. This is because they have, especially for larger multi-cores, this is because they have a higher reactance. So because the cores of the 3-core cable are quite close to each other, they have a lower reactance generally than a single core equivalent. Therefore, voltage drop is lower. However, the current capacity of a 3-core cable is lower than single core cables generally. Tip number 7, flexible conductors or flexible cables, be that copper or aluminium. In general, the voltage drop of flexible cables is higher by around, no, lower. I think it depends on the size. So for larger cable sizes, flexible cables, the voltage drop is generally the voltage drop of flexible cables is greater, but can be up to, okay. The voltage drop, because there's more strands, as you can see from the table, the voltage drop will be higher, but can be up to 10% lower for non-flexible cables compared with non-flexible cable for large cable sizes. The problem with these values, with resistance and reactance values of these highly flexible cables, is they're not well documented, especially aluminium cables. So we have obtained them from the manufacturers, and we've added them to our software, but they're not included in the standards. Especially aluminium flexible cables are not included. So you need to be wary of those. They're easier to deal with, but because of the higher number of strands, the voltage drop will usually be higher. Motor circuits. You need to, obviously we're running cables to motor circuits. The voltage drop should be based on the full load current of the motor, and we need to avoid a terminal voltage, especially during startup, of something less than 80% of the rated voltage of the motor. Otherwise, the motor may fail to start. There's a rule of thumb in the bottom of the slide that for DOL motors, consider starting and stopping, you should multiply the full load current by a factor of 1.4 for your cable sizing calculations. That's for a DOL, direct online motor. Just going to take a drink. If you have any questions, please include them in the chat, guys. Voltage rise calculations. Voltage rise calculations are exactly the same as voltage drop. There's no difference in the calculations. For solar applications, there is a voltage rise limit from the inverter to the connection point. So the AC side of the inverter, there's a voltage rise limit. If you follow that link, if you type that link in your browser, you will see there's some tables of the voltage rise limits for these sorts of solar installations. Fire conditions. Sometimes for buildings, critical power and control circuits need to survive fire, depending on the fire rating that you require: 30 minutes, 60 minutes, 120 minutes, 2 hours. It's possible to calculate the voltage drop for cables involved in a fire, like during the fire. It's around a temperature of 836 degrees that's used. So remember, I mentioned that as cable temperature goes up, voltage drop goes up. So that needs to be considered. If you expect the cable to operate or supply load during the fire, it will need to operate during that time at a higher temperature, much higher temperature. So voltage drop is going to be significantly higher. So in the absence of detailed calculations, you should increase the size of critical power and control circuits by 2, the sizes by 2, if they are expected to survive fire conditions. Conductors in parallel. This is very common. The main factor that we need to consider if we intend to use, multiple cables per phase or conductors in parallel, we need to ensure that there's equal current sharing between the cables of the same phase, or otherwise this could lead to overloading of one phase or certain cables. To do that, we must ensure that the conductors are of the same material, they are of the same cross-sectional area. This is obvious, but they also must follow the same route and be of the same length. If they're not, not going to share current equally. And they must be bonded in the same way. Also, the relative position. So we use equal spacing of the circuits within the groups, and we ensure they're parallel. The separation is symmetrical and consistent, and the phase arrangement is optimal. You can see on the right-hand side, we've got some configurations, multi-phase or multi-conductor configurations showing the non-optimized phase configurations and the equivalent optimized phase configuration, which ensures equal load current sharing between multiple circuits, multiple parallel circuits. You should use this table, especially for your installation. Now, remember that the standards dictate when you can, the minimum size when you can use conductors in parallel. They're actually very different. So the IEC standard doesn't allow you to use parallel conductors per phase for cable sizes below 50 square millimeters or 70 square millimeters for aluminium, copper and aluminium respectively. But the Australian standard allows from 4 square millimeters and up. So it's very different there. Okay. Short circuit ratings. Short circuit ratings are, remember I mentioned that's the third important factor for sizing cables. So power cables must withstand the short circuit conditions. It's rarely the case that short circuit conditions dictate the cable size, but in the example problem shown on the slide, there's an example where that is happening, and I'll explain in a second. But there is a relatively simple equation called the adiabatic equation. There is a non-adiabatic equation equivalent. The adiabatic equation is suitable for low voltage conditions. It gives you S min, which is the minimum conductor size that will withstand the short circuit current I for the time T. And it's appropriate up to fault clearing times of 5 seconds. Now your value K, you can either calculate K, or as in the Australian standard, there's a lookup table of Ks. So just match it with your cable type and the, I think it's cable type, perhaps temperature limits. But there's a lookup table where you can get your K value. But more accurately, we think it's more accurate and more flexible to calculate K, and the values in the equation for K are shown on this slide here. But you don't have to do it. You'll need the short circuit temperature limit to calculate K. I think that's what makes the Australian standard easier to use. Now on the right-hand side, you'll see a condition which does happen. We do get asked why it's happening. So for example, someone contacts us and says, look, I'm running 20 amps over 5 meters. And the software is telling us the minimum cable size is 16 millimeters squared. How can that be? I've looked up the table and I only need a 1 square millimeter cable to carry 20 amps, right? And we ask them, what's the fault level? And we confirm the length. Now, in this case, the fault level is relatively high and the length is low. So the fault current over the length of the circuit is not reduced by much. So therefore, the fault current or the short circuit current I is quite high. And therefore, the short circuit rating becomes the dictating factor. You can see in the diagram an image of our software where actually our software indicates the dictating factor. It tells you that the fault level is dictating the cable size, which is an important message for it to give you. Oops. Hang on a second. Neutral cable sizing. In general, it's recommended that the neutral conductor should be at least the same size as the active, if not the same size. But there are some rules and some differences in the standards for mostly for harmonics. So to protect against harmonics, I think it's in particular, it's very common to and mandated to use a neutral size of this, at least the same size as the active. But you can, according to the IEC standard, you can use a neutral conductor size smaller than the active as long as the harmonic current content is less than 15%. If it's between 15 and 33%, the neutral conductor size definitely needs to be at least the same size as the active. And if the harmonic current is above 33%, well, that's when the harmonic currents and the neutral size can start to dictate actually the active size. For multi-core cables, when you have high harmonic currents or high harmonic content, even above 15%, the currents in the neutral, the heating from the harmonic currents in the neutral actually dictate the active size too. And certainly for single core cables, when you have high harmonic current, you need to the neutral conductor size will actually be larger than the active. There's a table here which is taken from NZS 3008. It's only for 3-core cables. It's a little bit complex to understand. There's some paragraphs around it. But I think this slide helps. Earth cable sizing. There's different ways being used in industry to calculate cable sizes. Usually on the right-hand side, you'll see a lookup table. This is pretty common in Australia and the UK to use a simple lookup table for sizing your earth cables. It's based on the active cable size, and then you get a respective minimum earth cable size. But it's actually a simple way. It's not always, it doesn't always give the correct answer actually, and it's almost always conservative. The best way to size an earth cable is to actually calculate it. So to calculate an earth cable size, you need to consider earth fault loop impedance, and you need to consider the short circuit or the earth fault currents. And you also need to consider it can't be so small that it's not mechanically strong enough. So in almost all practical cases, when you calculate an earth cable size, it's almost always smaller than these simple lookup tables. Harmonics. So when the loads, when there are harmonic currents flowing in the circuit, these harmonics actually increase the average current of the circuit IB, or the RMS value. And the active conductor size increases as a result. So we do the root sum of the currents, the fundamental current and the harmonic currents to come up with an RMS, or an overall average current. And that should be used for sizing your active. It also has an effect certainly on the neutral. So when you have harmonic currents, especially third harmonic currents or triplet harmonics, you'll see significant currents start to flow in the neutral. So in the right-hand side, we've got some plots. So this is for a three-phase balanced, 100 amps on each phase, right? So at the top, you've got the phase current for the for one of the phases, one of the three phases, at 10% harmonics. So you can see the red line, top left plot, the red curve. You can see some distortion in the current plot, right? And then on the top right-hand plot, the red curve, you'll see some currents appearing, small currents appearing in the neutral with 10% third harmonics. So we've got an RMS current of 28 amps in the neutral with 10% third harmonics. And the RMS current of the phase conductor at 10% harmonics is a little bit more than 100 amps. As we go down, as we increase the level of harmonics in the circuit, we can see right down at 50% harmonics, we can see the neutral current actually exceeds the current in the phase conductor. And this obviously poses problems. If it's single core cables, the neutral cable size would be greater than the active size in this case. And at more than 15% for a multi-core cable, the neutral currents will start, or these harmonics will start to dictate the active size for a multi-core cable. Economic and energy efficient cable sizing. There is a method for this provided in the Australian standard. It's an optional method. We think it's a very good method, but it requires additional, as the designer, you need additional information, but you also need to be able to convince your customer, your client, to tolerate a higher initial cost. So when we size cables economically or energy efficiently, we're looking at the lifetime losses. So over the lifetime of a cable, a larger cable size will have lower electrical losses. It will get less hot, so it will waste less energy. So in theory, at the start of a project, if we increase the cable size above the minimum size to meet current capacity, those three factors, voltage drop and short circuit rating, if we take that size and we use a higher size than that, then that higher size will have lower losses. And over the lifetime of the cable, it's going to pay itself back, those lower losses. And there's a return, there's a payback period. And over the lifetime, it will be cheaper to operate that cable, but there's a higher initial cost. Another slight problem that you have as the designer is you need to make assumptions about interest rates, the cost of money now, dealing with the net present value cost. And you need to consider the cost of electricity now and in the future. Those are not very difficult things to work with. Probably the biggest issue you're going to have, the biggest resistance from that we see from users is that they need to sell it to their clients. But for operators, manufacturers who are just doing their own designs, I mean, they definitely consider the lifetime losses. So you can see an example here where the minimum cable size to meet current rating, voltage drop, and short circuit rating was 95 square millimeters. But when we do the economic sizing over the lifetime of the cable system, we've come up with the most optimal or economical size with a payback period of 3 years and 10 months is 240 square mils. which could be a significant cost at the start of a project, but over the lifetime, it's a cost saving. Like I said, economic cable sizing is optional. Let's look at a cable sizing example, which I will run through quickly in under 5 minutes before we'll take your questions. Let me share my screen. After this example, um, this hand calculation, which I will explain. I will also show you how to do it very quickly using software. I will bring up the slide where you can get your certificate. I will share the link to where you can access a free cable sizing calculator, and we will do your questions. So this example is a three-phase 400 volt system where the cable sizing is being performed for a high current load over a long cable run. It's 1200 amps. The length of the run is 260 meters. Single core cables, copper conductors, XLPE insulated at 90 degrees is the normal use operating temperature, buried in separate ducts. The voltage drop limit is 3.2%. The fault level is relatively high, but probably consistent for such a large system. This calculation is based on ASNZS 3008, but the same procedure, same principle applies to other low voltage cable sizing standards. So first thing we need to do is we need to find the minimum size to meet the current capacity. So 1200 amps. If we look at this table here, and we find the table that matches for XLPE insulated three-phase cables. That's this table 8 in this standard. Column number 27, we're also using copper conductors. So this column number 27 is the one we use. Now we need 1200 amps. So not even a 630 square mil cable can deal with 1200 amps. So we need to use at least 2 sets of parallel circuits. So in this case, we're proposing to meet current going capacity, we need to use 2 sets of 400 square mil. So 400 square mil cable is rated at 626 amps per circuit. So 2 times that over 1200 amps. So we're meeting current capacity with 2 sets of 400 square mil. Now that won't necessarily meet our voltage drop requirement, which was 3.2%. So most likely we are going to need to increase the cable size above that. So to do that, for the purpose of this calculation, we are providing you, because it's not really this simple in real life, 3 sets of 630 square mil cable. That's what we're proposing. You'll need to meet a voltage drop limit of 3.2%. So 3 sets of 630 square mil obviously meets current going capacity, doesn't meet the voltage drop requirement. We need to calculate the conductor operating temperature, because we will need that for our resistance. So here's the equation for conductor operating temperature. To calculate conductor operating temperature, you need the operating current, and you also need the rated current of the circuit. So 3 sets of 630 square mil are rated at 2,460 amps. We are operating those cables at only 1200. So what's the operating temperature? It's actually quite low. When you're operating that number of size cable at 1200 amps, the operating temperature will be only 40.47 degrees. Now we use that temperature to get our resistance value because resistance is temperature dependent. This is the resistance table from AS NZS 3008. It provides resistance at different temperatures. We are going to use the lowest temperature of 45 degrees for 630 square mils. This is our resistance value. We will use the resistance value for the voltage drop calculation. If you look along this row from left to right, 0.0389 and 0.0404, the values increase. As temperature goes up, resistance goes up, as I mentioned. We need reactance. We'll use a different table, table 30, for the reactance value. So now we have, this is the reactance table, single core cable, XLPE insulated, 630 square mil. This is the reactance value we need. Now we use the accurate voltage drop calculation or equation. I'm not sure if power factor was even mentioned in this problem, but no. So we are using a standard power factor of 0.9. This is the accurate voltage drop calculation. And we're using current, the length of the run, resistance, reactance, and power factor. We're calculating voltage drop, and as in volts, we convert that in percentage, 12.49 divided by 400, and we arrive at a percentage which is below 3.2%. So to meet current capacity, voltage drop requirements, 3 sets of 630 square mil over this long run. But we still need to check short circuit rating. So we mentioned at the start of the problem, 15 kA, 15,000 amps was the fault level at the start of the circuit. We are using the short circuit at the end of the circuit, so that will be reduced. How do we calculate the short circuit rating at the end of the circuit? We use the resistance and the reactance of the cables, conductors, and we calculate, so the fault current at the end of the circuit is 7,800 amps, which is lower than 15,000 amps. We use that in the that equation for K, or the minimum size to meet short circuit rating. We need the maximum temperature limit for that XLPE cable, 250 degrees. We need our K value. In this case, we're not calculating it. We're using the lookup table in AS 3008 to get our K value. Based on the initial conductor temperature, 45 degrees. Remember, our cables are operating continuously at around just over 40 degrees. So I think to be conservative, we're assuming at 45 degrees. And there's our minimum S. So to withstand short circuits, we only need a size something greater than 46 millimeters squared. Now we're proposing to meet voltage drop requirement. We need at least 3 sets of 630 square mils. So therefore, short circuit rating is not really a factor. It's not going to dictate the cable size. Neutral cable size, in this case, we're just assuming that we will run a neutral circuit, 3 cables of the same size as the active. Selecting earth cable size in this example, we shouldn't be using this method, this simple lookup table method, but you can use it. In this case, we're using 630 square mil. 3 times that, which is greater than 630. So we need an earth cable size of at least 25% times 3 times 630. But we do also need to check the short circuit rating of the earth cable. So in a nutshell, that's how you do it. Do the calculation by hand, but how do you do it using software? Now, I recommend that you note down this web address. elect.com/calculators. This has a bunch of free, these are professional cable sizing calculators. These are not toys. We are providing free access to Australian standard, British standard, New Zealand standard. The IEC standard is coming in a matter of weeks. So I recommend you write it down, elect.com/calculators. Let's open the Australian cable sizing calculator. This is our professional cable sizing calculator. You have access to the reports as well. So let's do it in this calculator. So 1200 amps, it's very, very fast. Power factor 0.9, 3 phases. Note that the calculations are instantaneous over here on the right-hand side. The length of the run was 260 meters. Fault level was 15 kA. XLPE, this cable sizing calculator includes all of the cable types, including aerial cables, for all of the standards. Copper conductor, we've also got copper flexible, aluminium flexible. Earth conductor, you can set it as copper or aluminium. That's not covered in the standards. Single core, I think we're using single core in this example. And then the installation conditions. So buried enclosure separate, I believe, for this example. So you've got table 8 here. And I will ignore protection, but it does, this calculator also has inbuilt errors, so it will tell you, the protective device is not suitable, etc. It has inbuilt protection. I believe the IEC calculator and the next iteration of this calculator will have inbuilt manufacturer protective devices. And you've also got all the details of the calculations here. The table and column number, you've got the operating temperature. You've got maximum length of run, impedances, resistance and reactances, and short circuit performance, fault loop impedance as well. So let me share this slide where you can get your certificate of attendance. I'll just stop sharing and then reshare. Just bear with me. And we can also answer your questions. So conclusions. Key areas of low voltage cable sizing includes current capacity, derating factors, voltage drop calculations, short circuit performance, neutral and earth cable sizing, additional considerations, harmonics, economic cable sizing. My recommendations to you are, I haven't shown it in this presentation, but it's really ideal to perform cable sizing calculations together within your electrical network. So it's better to model your switchboards and your electrical network because the fault level calculations, the voltage drop calculations are a little bit more accurate, and they're put into, they consider your electrical network. We have an electrical network calculator which automatically sizes cables based on your network configuration. Use accurate voltage drop calculations. Calculate minimum earth size rather than using simple lookup tables. Utilize derating factors from different standards, but consider the differences in the assumed standard conditions. Here's the final slide. So you can use this QR code on the left, your left, for the APAC. If you scan that QR code, do you have the link for the, I guess you don't have the link. I will also share the link in the chat for the form if you don't want to scan the QR code. And we can start answering your questions. Edston.
All right, so
Do you want to sit over here? share this mic today.
So we have time for a couple of questions. So the first question is, how do we decide whether to choose a single core or a multi-core cable? And is there a difference between AC and DC LV cable sizing?
Difference between AC and DC cable sizing, obviously the current rating will be different. So the current capacity for DC, when you run a cable at DC as opposed to AC, the current capacity is slightly higher for DC because there's no skin effect. You know, frequency is 0, so there's no skin effect or proximity effect. So it's okay to use the current capacity tables, which are intended for AC cables, to use those for DC. They'll be slightly conservative. And for voltage drop, well, our calculator has a DC setting, and that DC setting basically ignores the reactance of the cable. So voltage drop will also be a bit lower for DC cables.
Okay, the next question is, can we model a system without neutral?
Can you model a system without neutral? Turning off neutral, I'm not sure if you'd have to try it. I know you can turn off the earth. I'm not sure if you can turn off the neutral.
Yeah.
But if you can't, it's in our roadmap. Check it out. Try the calculator yourself.
And is there any limitations for a free cable sizing calculator?
Oh, there's no limitations to the calculations. No.
And if you want to fit a typical fault current value for different types of loads in Australia, how do we get it? Like, can we get it from the transformer or is it
Fault level?
Fault level? Yeah.
Can you get it from the transformer? Probably not. You can get it from the owner of the transformer, I would say. It's a little bit hard to get fault levels sometimes. I have shared the survey link. It's a survey link, but it's actually a form that you need to fill to get a certificate. We will actually email you a certificate with your name and the name of this course, etc. It's a professional certificate if you fill out the survey form.
The other one is for economic cable sizing. Do we consider extra cost with conduits, installation, etc.?
Yeah, so true economic cable sizing needs to consider all of the initial costs. So it's actually not just the cost of the cable. It's the cost of the conduit, if you use a larger cable size, even the higher cost of pulling a larger cable in, the higher cost of installing a larger cable. But installation costs are usually a bit harder to get. But ideally, you need to consider as much of the initial costs in economic cable sizing as possible.
Yeah. The next question is, how do we consider harmonics? Do we have a scaling factor or something for this in our software?
Our software, our LV network calculator, we are soon to introduce harmonics. That's in very soon in one of the next releases. So we even have a harmonics load library. So there's no easy way really to consider harmonics. It's fairly complicated calculations, but we are making it easy in our LV network calculator in one of the next releases very soon.
Yeah. I think we'll take one more question. How important is the MCB curve type on earth loop impedance?
On earth loop impedance?
Yeah.
Yeah, I mean, it makes a big difference what type of MCB you're using, and does affect the fault loop impedance, which in turn impacts the earth cable size. There is an article on our website. If you just go to Google and you Google fault loop impedance, you'll find our article, which fully explains and includes the MCB protective device information.
Yeah, just one more question. So someone has procured some cable from overseas, and it gives all the data at 30 degrees, the current rating at 30 degrees, but Australia is at 40 degrees. So how do they manage that?
Well, I guess it's relatively simple. Obviously, cables need to comply here. You know, there are other Australian standards like 5001, etc., for your cable requirements in Australia. But if it's merely the rating that you're talking about and it's been rated at 30 degrees, well, you can just use if it's a low voltage cable, you can just use the derating factor table for ambient air temperature or ambient soil temperature that's provided in AS 3008. Just increase the assumed operating temperature.
Yeah, I think we'll answer that.
Thank you so much. We've gone a little bit over time. I really hope that everyone's got something out of this technical presentation. We really do try to deliver value. I thank Edson for his assistance, as always. Thank you for your time. And we really hope to see you on the next technical presentation. Thanks, everyone. Thanks for joining. If you have any further questions, you can please reach out to us at Elec, support@elec.com. Support@elec.com. We'd love to hear from you. Thanks, everyone.